This is Ibanez metal charger, and it is not what this video is about, but it's a start. I bought this metal charger recently, and it was kind of a random purchase. It looked intriguing, and the price was right. It turned out I quite like it, which inspired me to take another look at the Ibanez pedal lineup from this era. Frankly, I think the list isn't particularly exciting, but Mostortion caught my attention. It is subnamed MOSFET Distortion, and it looks like a somewhat unique take on distortion. I thought it would be worth looking to buy one. I quickly discovered that it's less common and likely held in higher regard than the metal charger. First off, there was nothing listed for sale in the domestic used market here in Poland. When I looked across Europe on eBay and Reverb, I could find 2 or 3 listings, but the price was about 6 times what I paid for the metal charger, which is too expensive for me, at least for this kind of pedal. Then I thought maybe I could build one. Apart from the much lower expense, a DIY build might be fun, and you can tweak things to your liking. Now, if I want to go that route, I have 2 options, PCB or strip board. I don't like PCBs, I mean, for DIY, not in general. It's usually more compact and less work, but you're locked into a specific design and often into specific parts. There just isn't much room for modifications. Plus, you need to find a shop that sells a particular PCB. I did that once and it wasn't a good experience. In the end, it felt like buying a chair from IKEA. Like I bought a ready-made device that I just had to assemble myself. It took away most of the sportsmanship from the whole affair. So, strip board it is. Now I need a layout. I could make one according to the schematic, or I could search for a ready-made one. In this case, that is, a blind build, where I don't know what the end product is going to sound like, I'd rather use a ready one, especially if it is verified to work. I have found these 2. Links to the respective layout blogs will be in the description. I assume the original Mostortion is packaged the same way as metal charger, that is, Boss style, with buffers on input and output and an electronic bypass switch. The layout on the left includes buffers, while the other one doesn't. I prefer no buffers. I don't see the advantage of having buffers in a home studio situation. I can always add a buffer later using a secondary board. Let's have a closer look at the layout. So, it's a dual op amp with clipping diodes and a tone stack. I think I should already have all components except for some potentiometers and a chip. The chip is the CA3260, described in the datasheet as BIMOS operational amplifier with MOSFET input and CMOS output. It looks like it has been discontinued for years. It has a standard pinout, so you could replace it with a TL072, for example. But since the whole effect took its name from the chip design, I think it's essential to get the original. So I'll make a pause here and see if I can buy one. Well, that pause took 2 months. Turns out it's rather rare. I found nothing in the domestic market in Poland. eBay had 3 listings in Europe, specifically in Italy, Germany and France. Different manufacturers, priced at about 5 to 10 euros for a piece. I bet on one from Germany, but it wasn't a lucky bet. First, the seller took a long time to respond, then I had an awkward conversation about my address. After a week, it was marked as shipped. So far, it hasn't arrived. After 3 weeks of waiting, I gave up and ordered the one from France. This time, there was no problem, and it arrived within a week. And here it is. Manufactured by Harris Semiconductor in the 41st week of 1990, if 1941 is the date code. Mostortion was produced between 1990 and 1993, so it matches the period accurately. Now that I've secured the most crucial component, let's get back to the layout. Let's see if I can identify the different parts and points of possible modifications. Here's the polarity protection diode and the power filter cap. A standard addition in DIY layouts. Not always true to the schematic. I once fried the chip on a circuit that had no protection diode. I had a mooger-fooger and regular pedal power supplies lying on the desk, which have different connector polarity. I grabbed the wrong one, so I now recognize the importance of this diode. Here's the input capacitor. I think I will leave it out of the initial board to try different values. You can often adjust the input filter for more or less bass by using smaller or larger cap. I usually prefer less bass. We'll see. Here are the clipping diodes. I'll definitely want to experiment with this part of the circuit. They're essentially connected across the drive pot lugs, so I can use an additional external board with sockets and connect it to the pot to avoid desoldering on main board. There is also this small cap likely to filter high frequencies. I like keeping as much high end as possible, unless it is causing self-oscillation. So I will use a socket here too and experiment. These two caps likely define the range of the mid-tone control. I'll leave them as they are. Then, this 330p cap is connected to the treble tone control. I think I will want to experiment with the cap value, since I usually prefer a brighter sound. I'll put a socket here as well. I have 4 elements to tweak. Maybe it's enough. So, I'm going to assemble the rest as is. Now I need to cut a piece of the board so it matches the layout dimensions. The layouts are usually made to be compact. In a situation like this, where I'm considering modifications, I find it desirable to add some extra space, maybe 4 or 3 columns. This way, I can avoid possible desoldering of components. For example, if I use a socket and then decide to use a specific part, I can just leave the socket in and solder the part next to it. At this point, I should check if the board will fit the enclosure. Here are 2 common enclosure sizes, 1550B and 1550M. This layout would fit in the smaller one. Adding width could be a concern, but I'm going to use the bigger enclosure anyway. The reason is the number of knobs. There are 5, which I think is too many for the smaller one. You could likely fit 5 or 6 pots in there, but then it would be too cluttered to operate them comfortably. Here are 2 DIY pedals that I made, using the 1550B and 1550M enclosures, placed next to the metal charger, and a Boss pedal for size comparison. As you can see, there are 5 knobs on the metal charger, all in a very small space. I am a tweaker. I like to adjust things, and I hate these tiny knobs. Okay, so here's the board. I marked the cuts on top and used a metal drill bit to cut the tracks. The marks make it easier to navigate the board when attaching parts. Now I will make the links. Whenever I trim a component lid, I save it for later instead of throwing it away. So now I have a pile of them. Perfect for making links on the strip board. The links are soldered. I also marked the ground and power supply paths. It will come in handy later if I need an extra ground or an LED supply connection. I will now connect resistors and the supply diode. I never had patience to decode resistor color codes. I just measure everything with this chip tester before soldering the components. This way, I have some confidence that they are the correct and working parts. I used Dale precision resistors whenever I had ones with the correct value. These resistors are rather expensive, but it's the beauty of DIY. You can go overboard, even if it's unnecessary or not practical. Next, I attached the sockets for the chip and the 330p capacitor. I will use external board with sockets for clipping diodes and a small filter cap. Now the small capacitors. They have already been measured. Ones in the middle are polypropylene. The yellow one and the red one are polyester. Here's the board with the caps attached. You can see that I mounted the blue 33N one horizontally. That's because vertical space is usually scarce in the enclosure. Keep in mind that the board usually goes on top of potentiometers. So I always try to make it as flat as possible. Now the large caps. Black ones are 1 microfarad MKT polyester. The blue one is 100 microfarad Nichicon electrolytic for power filtering. The gold one is 47 microfarad electrolytic, also a Nichicon. I usually try to avoid electrolytics, except for the power supply filter. I'm not quite sure what the 47 cap is doing, but at this value there's no alternative anyway. And here's the board with all caps attached. Again, I try to keep it flat. Now I'm going to attach wires and potentiometers. I use these solid core copper wires. They are actually rather difficult to buy here. Every store is flooded with silverish wires from China, which tend to break the second time you twist them. I also prefer solid core wires over stranded wire because they stay in place and provide support for the board and loose parts like LEDs. And there it is. Time to find out if it actually works. This is what I call the testing terminal. It's a kind of interface with input and output jacks and power supply plug on one side and crocodile clips on the other. It makes it easy to test a circuit board without a proper enclosure. The thing is, when you take the enclosure, jack sockets and the foot switch, that's usually the most expensive part of the build. On the other hand, my success rate when building random effects is roughly 50%. Half of the time I get something interesting. Half of the time it doesn't work at all, or it sounds horrible. So I learn to make sure what I build works and is interesting enough to be worth the effort of preparing the case. And do it before I even consider unpacking the enclosure, let alone drilling into it. And so I built this, and it proved to be an essential tool in my DIY adventures. I have sockets for banana plugs here. Then I use these cables to connect to the board. And you can stack these banana plugs, which is very useful. I also made a switch to swap the ground and power supply, so I can use it with germanium fuzzes. Alright, so let's connect the board. I also need to connect the input cap. For now, I will use this 1 microfarad polycarbonate cap. I'll use a crocodile clip to attach it to the board. The circuit is currently missing the clipping diodes, the filter cap and the treble cap. But it should make some kind of sound. Let's not forget to insert the chip. The guitar is now connected to the terminal. The signal then goes to my DI box and then directly to my audio interface and digital workstation. And now, time to flip the switch. It's the moment of suspense. So many times I've flipped the power on and then nothing's happened. Usually I could then figure out what was wrong, but it's an awkward feeling when it fails on the first try. Alright, we've got sound. Great. The drive, bass, mids and trebles are all at maximum. I think we're missing the trebles, I should put the 330p capacitor into the socket. Here's a Styroflex one, so we're going for a hi-fi build. It has tiny lids. Hopefully it won't fall off the socket. I've put oscilloscope and frequency analyzer on screen so we can monitor the waveform shape. I think it sounds rather fine with this 330p capacitor. Many classic distortions sound somewhat muffled to me, but this one, I like it already. However, since I preemptively installed a socket, I feel obliged to try other values. Let's check something a bit larger and something a tad smaller. These two capacitors are 220 and 510 picofarads, both silver mica. For the test, I'll keep all tone controllers at maximum. The guitar I'm using is a modified Codin Stadium HT bridge pickup, which is a DiMarzio DP 389. It's a humbucker in single coil size. It's quite loud actually. Let's start with the larger 510p capacitor. Now let's check the 220p capacitor. All of them sound fine to me, offering slightly different flavors. But I think I'll keep the 330p. Interestingly, there's quite a lot of distortion here, even though I haven't connected the clipping diodes yet. Which reminds me that I have seen people arguing online that the op-amp doesn't matter in this circuit, because all the clipping is done by the diodes. For example, here's a quote from the description of a Wampler pedal advertised as a tribute to Mostortion. One of the original Mostortion's little-known secrets is that it doesn't actually use MOSFETs for its overdrive. It uses a MOSFET-based op-amp, but it uses clipping diodes to produce distortion. So I don't know. Maybe I've got something wrong in this build. Anyway, let's keep it without diodes for a little while. I think it may be a good moment to check different, somewhat random op-amps, see how they will behave as a drop-in replacement for the CA3260. Here's what I'm going to try. TL072, described as low-noise, JFET operational amplifier. It's very common. It should be very easy to find. CA3240. It seems closely related to 3260, described as BMOS operational amplifier with MOSFET input and bipolar output. It has a different output stage and a wider supply range, up to 36 volts. Unlike 3260, it's rather easy to find. ICL7621, described as a low-power CMOS operational amplifier. It has a much slower slew rate than other three, which is not necessarily a bad thing for a guitar fuzz, as proved by the ret. It's fairly easy to find, although noticeably more expensive. So I'm now going to play some short phrases and cycle through these op-amps. Maybe I should normalize the volume of the samples, since loudness deeply affects how we perceive sound. But I wanted you to hear the difference in output volume, which matters, since we're going to add clipping diodes. Anyway, here are my thoughts. The TL072 sounds entirely different to me. It also responds differently when you play, which you can't figure out just from listening to samples. The ICL7621 is somewhat close in character, but it doesn't have that sparkling top end. The 3240 is quite close, but as you've probably noticed, the waveform is asymmetric. I mean, it has large offset. Just look at the clips. Possibly that could be fixed by adjusting the circuit, but it doesn't quite work as a drop-in replacement. Then, if you remember, the 3240's maximum voltage rating is higher, specifically 36 volts, compared to 16 volts in the 3260. So it's more than double. Which makes me want to try running it at 18 volts, which is a sort of secondary standard in pedals. I remember some people claiming that JFETs sound better at higher voltage. Maybe it would translate to MOSFETs too. However, the weak link in my build is the 47 microfarad electrolytic capacitor, which is only rated to 16 volts. In the end, I couldn't resist and tested it at 15 volts, just to see if there's any point in exploring it further. Let's compare the results to the 3240 and 3260 at 9 volts. First, let's look at the clips. As you can see, the offset is still there, although not as large as at 9 volts. Running it at 18 volts could just do the trick and remove the offset completely. Now, let's hear the results. This time, I adjusted the loudness to keep all samples at a similar level. So the 3240 sounds pretty much the same at 9 and 15 volts, apart from the offset and loudness, and it sounds different from the 3260. I should also mention that at 15 volts the 3240 was much louder than the 3260. In the end, I think it might be worth a try, but it would be a different build and a different sound, so maybe another time. Let's now look at the clipping section. Here's how it looks on the schematic. We have a distortion potentiometer, a 56 picofarad capacitor, and a set of diodes. In the layout, the diodes are 1N4148s, a standard silicon switching signal diode. In the original, however, they used MA165s, fast-switching Japanese diodes. I think these are out of production, and in Europe they are actually harder to find than the op-amp chip, so I didn't pursue. Anyway, for clipping, silicon diodes tend to sound the same as long as they have similar forward voltage, at least to my ear. Through internet research, I've found that people measured the MA165 to have about 0.7 volts. In distortion pedal clipping, forward voltage translates to the depth of the cut. Smaller forward voltage means deeper clipping, which means more compression and more distortion. When you connect two diodes in series, forward voltage adds up and you get a louder but softer sound. So in the case of Mostortion clone, we should then aim for 1.4 volts of forward voltage. Though I'm tempted to try other values too. I will measure the diodes with the Atlas Peak semiconductor analyzer. Let's check the 1N4148s. They all read about 0.69 volts, so it's a match. Now let's pick something to compare it with. First off, I'd like to verify it against another silicon diode and check if they really sound the same. Here's a BA114, a vintage European silicon diode, which measures 0.7 volts of forward voltage. Then let's compare it with a germanium diode. This is a OA172 high-frequency diode. It reads about 0.69 volts, slightly varying from unit to unit. Since we're trying different chemical elements, 1.4 volts forward voltage is in the range of a single LED diode. However, there's no direct match. Red LEDs, which I have, measure 1.8 volts, while infrared LEDs measure 1.1 volts. I'd still check the red ones. Actually, maybe also the blue ones. Blue LEDs have high forward voltage. This measure 2.6 volts, so we can check what happens when there's much softer clipping. Also, how about combining infrared with germanium? Here's a D311, a Soviet germanium rectifier diode, which reads 0.27 volts of forward voltage. Add 1.1 and we're in the realm of 1.4 volts. Then I'd like to check how it sounds with harder clipping. So, let's try replacing each pair of 4148s in series with a single 4148. Finally, let's check something bonkers. I feel I should use at least one part that was actually made in Japan. Here's a vintage power supply rectifier diode made by Hitachi. And let's just use one to try asymmetric clipping. So we have 8 options to check. I guess I will need to reduce the number of test phrases, or else this video will exceed Bollywood standards. Now I will need a socket board. I made this. On the left side, I have a socket for the capacitor, and on the right, there are sockets for diode pairs. For now, I will just solder it to the distortion potentiometer lugs. There we go. I will test the capacitor later. Let's start with diodes. Again, I will play short phrases and cycle through different diode sets. Here are my thoughts after this test. First, this thing is very loud. I expected the output volume to drop after connecting the clipping section, and it did, but not as much as I thought it would. I have the effect output connected directly to a digital audio interface, therefore I need to have the volume in check to avoid clipping at the analog to digital converter. In my setup, a distortion pedal, like the metal charger for example, will usually have a lot of headroom even when the volume is cranked to the maximum. In this build, with the clipping diodes disconnected, I had to set the volume to about 1/3 to keep it at a safe distance from the clipping threshold. And it still would be about twice as loud as the metal charger. After adding the silicon diodes, the signal level dropped a bit, and I set the volume at about halfway. So as I said, it is loud. Now about the diodes. The germanium set just doesn't work here. I also didn't like the single 4148s much. The double silicon set sounds good to me, and I'm sure I wouldn't be able to tell a 4148 apart from a BA114 in a blind test. Note that I played each test phrase live, so the takes may sound a bit different, especially with muted notes. But if you just listen to open notes, they sound the same, which tells me it's probably not worth the effort to chase the original diodes. I also liked LEDs, both red and blue. The LED germanium set was also fine, though similar to just LEDs. It was a bit smoother on the top end, but I'm not sure it's different enough to make it worth an option. I think the Hitachi one delivered. It sounds delightfully over the top. In the end, my favorite setup is the one with no diodes at all. For the final build, I would like to have at least 3 options. No diodes, double silicon, and one of the single LEDs. For 3 options, where one is no diodes, I can use a single pole 3-position lever switch like this one. Then in the middle position, both output lugs are disconnected, and that would be the no diodes option. But I'm quite tempted to have both LED colors, as well as the bonkers diode. I would then need to use a rotary switch like this one. Alright, so what's next? I should check how tone controllers work, try different input capacitors, and then decide how to approach the diode switching situation. But first, let's see what the function of that small 56 picofarad capacitor is. It's the capacitor I haven't connected yet. I have a 50p silver mica capacitor here, so I will put it in the socket and compare the sound with and without it. By the way, if you search for a shot of the original Mostortion board, you can see they used a ceramic cap. It's right next to the diodes. For this test, I will change the guitar to this S-series Ibanez and remove the clipping diodes. So this capacitor removes that high-frequency fizzle sound. I swapped guitars because it wasn't that apparent with the other pickup, but I really like the fizzle. I guess I'll need to add another switch to make it optional. Now let's look at the input capacitor. The circuit sounds fine to me, and I suspect I'll keep the capacitor as is. But since it's still on crocodile clips, let's see what happens if I use smaller values. Now it's 1 microfarad, let's try 100 nanofarads and 10 nanofarads. For this test I will use the classic setup, 4 silicon diodes and filter cap. As before, all tone pots as well as drive are set to maximum. I can't hear a difference. Except, with the 10 cap there is a background hum, which seems to depend on capacitance. Let's check 1 microfarad against 10 nanofarad and 1 nanofarad. No playing, just the background noise. So I'm going to keep the 1 microfarad cap. I think I will now solder all socketed capacitors to the board. The input and treble capacitors are in, and the fizzle capacitor is in. I also connected a switch to be able to turn it off. Now let's hear what the tone and drive potentiometers do. I keep the fizzle cap enabled and the silicon diodes in sockets. As you could hear, adjusting the tone pots greatly affects the volume level, which is not ideal, but overall, the tone section is quite useful. I usually hate tone controllers in pedals. This one is definitely better than average. After this test, I swapped the treble pot from logarithmic to linear, as it would get to the muffled highs very quickly. The linear one suits me much better. Let's move to the clipping diodes. I think I'll go for the full set, that is 4 sets of diodes plus no diodes, so I will use 5-position rotary switch. I'll also need an extra board, because there's no way to fit all the diodes into my main board. Anyway, it will be more handy to have the diodes placed next to the switch, which will be easier with separate board. And here's my clipping board, trimmed and cut. And now, with the silicon diode set, red and blue LEDs, and the power diode. Finally, let's connect the switch. Let's test if it works. For now, I will solder it to the drive pot. By the way, here's why it is a good idea to keep the input wire away from other wires and components. The same thing will happen if you route the input signal too close to the output path in the board. The effect is particularly apparent when the wires are placed in parallel. I guess the sentence, "Symmetry is the aesthetics of fools," is quite accurate when applied to distortion builds. Anyway, when I place wiring in a pedal case, I try to avoid parallel lines if possible, and choose diffused chaos instead of an organized tidy structure. So, I think the build is done. Everything is connected, and I quite like the effect. I can now move to the next stage and put it in an enclosure. However, this video is already fairly long. I think I'll end it here. Possibly I'll put another video documenting how I'm going about tailoring the case for this circuit. Maybe I'll see you there.